by ourselves. But in practice, we have 1,000 of points. It's impossible that we can manually identify what is W, what is B, right? So in practice, this is more like a real-world case. You have a lot of points for each class, and I want to find a line that can separate two classes and can have largest margin. And in this case, it's difficult that we manually identify. So we need some automatic way that the computer can automatically figure out the best line for us. So that's why this is the separated line, and we have 3 support vectors. The question is, how can we figure out the best W and the best B? Right? So this we need an optimization tool that can help us find W and B automatically. So this is a mathematical formulation. So here, right? So we have suppose we have n positive points, x1 plus x2 plus xn plus. And then m negative ones. So xi plus xj minus. I mean, because we are talking about we have a training data set, right? Suppose the training data set, we have x1, so this is x1 plus x2 plus x3 plus to xn plus. So we have a capital N positive points. And then we have x1 minus, x2 minus, x3 minus to xm minus. We have m totally negative points. You think about there are m black points, there are n red points. Because again, I'm talking about now we're going to use the symbols. So you need to get used. So each symbol is a point. And so in order to find a best line separate these two classes, this maximum margin, right? So we can formulate this as this optimization problem. Because this is the margin, right? I want to maximize the margin, and I want to make sure all these positive points are above w dot x plus b equal to 1. Right? So here, all the red points. So here we define red class is positive. So I define all red points are above this w dot x plus b equal to 1. And then all black points are below w dot x plus b equal to minus 1. You follow? Right? So that's why, so this is above and then below w dot x plus b equal to minus 1. Why? Because between plus 1 minus 1 should be one margin, right? Should not include any points. Okay? So which means as long as all red points, all positive points are below, above 1, and all black points are below minus 1, this must be satisfied to ensure this is the margin, right? Marginal space, no points within. So under these conditions, I want to maximize margin. And because this is W2 norm, right? So W dot W square root. So for this reason, the maximization is equivalent to maximize W dot product W. Can you follow? Because I want to maximize inverse of W, right? Which is equivalent. Let me write here. Maximize W B to W is equivalent to maximize W B to W dot W square root. So W dot W is a W1 square plus W2 square. Can you follow? And this is equivalent to maximize. Two is a constant. We just set as a constant equal to 1. W dot W.
The same as like minimize.
Because the square root is a monotonic function. You remove square root, it's a monotonic function. It will not affect your optimal solution. So please write the notes. It's important, especially if you did not take any optimization course before. And then maximize 1 over something is equivalent to minimize the denominator. And because W dot W is a W1 square plus W2 square, so this is a quadratic function. Right? So basically, the objective function you want to maximize is a quadratic function. And the constraints are linear. Okay? So this is why maximize a quadratic function subject to linear constraints.
So
minimize. Yeah.
So the meaning of the first line, the maximize W comma B equal 2 by W norm. That means like we have to maximize 2 by W norm, right? And
2 over W2 norm.
Right. And like set W and B in such a way that it gets like maximized. That's what it means, right?
Yeah.
So B has no effect on 2 by W norm, right? So
But the B affects your linear constraint.
okay.
You cannot randomly set a B because you need to set a B. Make sure all positive points are above positive 1.
Okay.
All black points are below negative 1.
Oh, so that's a part of the constraint.
Margin is only decided by W, but the B affects your linear constraint. Okay? Any question? So here, that's why we want to minimize a quadratic function, right? W1 square plus W square subject to linear constraint. Keep in mind, x1 plus xi plus xi minus, they are given, right? Only W and B are ungiven, are unknown. Okay? So this is called this name called a QP problem, called quadratic programming. And there's a tool, there's a toolbox that can solve all quadratic programming problems. You can just Google, easily find. So which means you do not need to worry about how to solve this problem, because this is a standard quadratic programming problem. There's some library. You give this as input, it will automatically return W. That's all. Okay? And if you want to know, how exactly, the library or optimization tool can somehow find the optimal WB, then you need to take an optimization class in the mathematics department. Okay? So that's all, right? So in practice, right, when you apply a library, Python library for SVM to do training, the library internally is to apply a QP optimization tool to solve this optimization problem, and then return W and B. So now, this is equivalent to minimize. Suppose we can solve the problem, we can find W and B. Right? So how can we identify support vectors? You search for points such that either equal positive 1 or equal minus 1, right? Because this is the boundary for positive space, right? This is the boundary for negative space. So equal to 1, equal to positive 1, equal to minus 1, as long as the points satisfy one of the two equations, then the points are called support vectors. You follow? Question? Yeah.
What if it is 0, like WX
It cannot be 0 because here, right? So if this is equal to 0, which means the point is in the right line. But it's impossible because the margin should not include any points for sample case. Right? So which means if you find some training point, you calculate W of x plus b equal to 0, then something must be wrong. Okay? Which means W and B definitely something is wrong. Because the margin should not include any points. So which means all your points either equal to 1 or above 1, or equal to minus 1 or below minus 1. Cannot be between. Any other question?
So they have more than 3 points which are support vectors.
So suppose we only have a 2 dimension, right? So far, all the examples we have 3 points, right? And it can be 3 or 3 more, right? And if we, so if we only have a 2 dimension, maybe 3 could be enough. But if we have 1,000 dimensions, not a 2 dimension, then you have many more. Okay? Any other question? Great. So by the way, right? So if you apply SVM library, and then there should be a function that can return support vectors. You should know, the library returns support vectors actually is a scan all the points and identify the points that satisfy one of the 2 equations, right? And when we will apply SVM to predict positive class, you should know this means W dot x plus b is greater than 0, right? You should know the fundamental. Great. So now, intuition of support vectors, right? So support vector machine, right? So support vector machine, support vector, right? Why support vectors are so important? So this is an example. And suppose this is a solution, we have 3 support vectors. So which means this point satisfy equal to plus 1. These 2 points satisfy equal to minus 1, right? So which means, I mean, after you train the model, you identify support vectors. Then you can disregard all the other points. Only keep your support vectors. And then you apply your classifier to train your model, you get exactly the same solution. So basically, support vectors are the points that can summarize all your data for classification. That's all. So which means I can remove all the points. And then you apply, so you only have these 3 points. You solve this problem, then you get exactly the same W, same P. So this is why we call it support vector machine, right? Because support vectors are the points that beside your line. Okay, so this is the application for tweet classification. Because I mean, for a cross project, somehow you need to build a classification model so they can classify tweets to positive or negative, right? And suppose we consider 6 dimension. We consider frequency of accident, feature 1. Frequency of slow, keyword slow. Feature 2, frequency of keyword traffic. Feature 3, soccer frequency. Feature 4, grandfather. Feature 5, Pittsburgh. Feature 6. I mean, I only define frequencies of 6 keywords, but you can define 1,000 keywords. Then you have 1,000 frequencies. Then your feature X will be 1,000 by 1 dimension, right? 1,000 by 1 feature vector. Then W will be 1,000 by 1. So 2-dimensional space, W only have W1, W1, W2, right? So you have a 1,000 dimensional space, then you have a W1 to W1, W1,000. Plus B, so which means, suppose you have 1,000 keywords, then W has 1,000 parameters, B 1 parameter. In total, you have 1,001 parameters that you need to estimate. And then you estimate W, estimate B. Then for any tweet, you can calculate frequency, right? Then so suppose you know frequency, you know W, you know B. Then if this is positive, then you say this is positive tweet. And this is negative, then this is negative tweet. So this is how you can apply SVM to do classification. Very cool, right? So let me give you an example. Suppose, right? Suppose we estimate W and B. Actually, let me write it here. Accident. Slow. Traffic. Soccer. Grandfather. Pittsburgh. Suppose you estimate W. So W is 0.6, 0.1, 0.3, minus 0.6, minus 0.9. Oh, SOCA, 0.7, minus 0.9, minus 0.6, and then minus 0.5. So this is your B. This is W. Okay? So if you can estimate W and B, right? Then suppose this tweet, right? So you count what is frequency of accident. Here frequency 1, right? So this is equal to 1. How about frequency of slow? No, right? Equal to 0. Traffic.
There's
One.
one slow, so slow should be 1. The second line.
Second line?
Yeah, slow traffic.
Oh, slow. Yeah, you're right. Equal to 1.
Traffic 1.
and then traffic equal to 1. SOCA, how about frequency SOCA? 0.
No, 0.
How about grandfather?
0.
0. Pittsburgh? 0, right? So which means,
1.
so what we have is .6, 0.1, 0.3. One, 0, 0, 0, minus 0.5. Right? And then we'll calculate, is this positive or negative?
Positive.
Because this is equal to 0.6 plus 0.1 plus 0.3 minus 0.5. So we have 0.5. Right? Positive, right? So for this reason, we predict this tweet is positive. So it is related to road traffic. Okay? So we apply, right, a support vector machine to classify a tweet to be positive about road traffic related tweets. Internally, this is how SVM make decision. So here we have a 6 dimension, right? But of course, right, I mean, 6 keywords are not enough. In practice, you may need 500 tweets or 1,000, sorry, 500 keywords or 1,000 keywords. Then this will be 500 by 1 feature vector. Okay? So I hope now you have an idea, right? I mean, what is the internal functioning of SVM to make a prediction for a tweet? So this is how it works. Let me try another tweet. So this is positive. How about this tweet? So what is the frequency of accident? The program was excellent and informative. I cried. It was even better than my last 2 or 3, my grandfather on traffic school. So that's no accident, right? 0. How about frequency of slow? 0. How about traffic? 1. How about grandfather?
1. Oh, soccer.
Soccer?
Yeah, 0.
0. Grandfather 1. How about Pittsburgh? 0, right? So what do we have? 0, 0, minus 3 plus 0 minus 0.9 minus 0.5, which is minus 1.1. Right? So then we say this is negative. And 1.1 is larger than the previous one, right? So which means this tweet, we are even more confident than the previous one. We can predict this is negative. I mean, if you think about W, it's kind of each feature you estimate weight. Okay? If the weight is positive, which means if you observe this feature, it will give you big plus to be positive. If the weight is negative, then which means the feature will give you minus, will make this more likely to be negative. And then your final prediction is kind of weighted summation of all your features. And then B is kind of an intercept, like bias. Okay? Bias adjustment. So this is how support vector machine works, right? And again, right, so far we talked about linear. So nonlinear, you'll find out similar, but let us focus on linear, because if you are familiar with linear, then it's easy, we can generalize to nonlinear. Okay? Very cool, right? So you have an idea what is functioning of a support vector machine. The last one, negative. So that's why, in order to make the support vector machine classify work well, so you should have meaningful features. And for example, right, grandfather, grandfather, is this important feature? why a tweet why a mention of grandfather will have a bigger penalty for the tweet to be positive. I mean, this may not be a good feature, and we don't know. I just a random example. Right? So some features may not be very useful. So you should have a meaningful features, and then you need to estimate WB, right? W is kind of the weight of the features. B is the bias of your classifier. Okay? Great. So we finished the linear classifier. Actually, we finished the separable case for linear SVM. So now we are talking about inseparable case. So what do you mean inseparable? So which means you have some training data, you can never find a line that can completely separate two classes. It's impossible. Okay? This is called an inseparable case. So how can we handle inseparable case? So this is next part. So basically, I mean, as we have this is separable case, right? You can find a line that is separate two classes easily, right? Easily. And again, how to find a WB? You maximize margin. Make sure all red points are above +1, all green points are below -1, right? So these are the constraints. So what is a non-separable case? So the basic idea is, suppose you have this support like machine, right? So this is your separating line, and then +1 is going up, this positive space, this negative space, and then inseparable case, which means you have some red point that is a wrong space. Okay, this is red, right? It should be above this red line, but unfortunately, this is in this negative space. Okay, this is an example of a violation of separation. And so, I mean, before we talk about how to handle this non-separable case, so we need to somehow measure the classification error. Okay? So the classification error in this case can be measured based on the distance of this red point to the red line, +1. Because if the point is above this line, the distance should be 0. And if this point is below the red line, so this length basically tells you how much violation, how much error the current classifier predict x0 plus. And the distance can be, if you remember, can be calculated this way. Okay? And we consider this numerator as epsilon 0 plus, and denominator as keep this form. And then we consider another case. So in previous case, we have a red point that is in the negative space, and then we have green point that is in the red space, and then we have this error, right? This is the error for this point. So this is the error for this point. And the error for the second point is W, by the way. It should be minus. Okay? So this is the error of the second point. So we have two examples. One is a positive point is in the negative space. We have an error. This is the error. And then we have a negative point in the positive space. This is the error. And then to make our life easy, because all this error, the denominator is constant, right? They're all the same. So we just remove the constant. We only keep this the numerator part. So we consider that the denominator is constant for all distances. We consider a similar form. So which means the area of the current support machine for this red point is epsilon 0 plus. And then the area of this, the current support machine for this negative point is this distance, is epsilon 0 minus. Okay? And this is the equation. So which means the distance tells us how confident we can classify a point. The distance can also tell us what is the classification error if a training point is in the wrong side of the classifier. Okay, so now examples. So this is a non-separable case, and we only have one violation of point. So in this example, can you find a line that can separate two classes? Impossible, right? See here. So which means, in this example, the data is not separable. So if you can find a line that completely separate two classes, then it's called a separable case. So this is called a non-separable case. Okay? So how can we handle this one? So how can we reduce the error? Any suggestion? So this is the error, right? So how can we reduce the error?
Should move the line closer.
Yeah, we move this line closer, right? Then this error will reduce. Right? Okay? So we move the separated line closer to the right point, to this misclassified point. Then this error is reduced, right? You follow? But what is the sacrification? The margin is reduced, right? You follow? Okay, so this is the trade-off. So in order to reduce the error, I need to move this line closer to this point. If I move closer, then the margin will reduce. So this is only case one. We only have one misclassified point. How about if we have multiple misclassified points? How about this case? So basically, the good news is the error. The error is this is epsilon 7 plus. The error reduced, but the bad news is the margin also reduced, right? So now we consider a little more complicated case. So we have three misclassified points. Two are in the red space, x5 minus, x8 minus. So this should be in the minus space, but they're in the wrong place, in the positive space. And then x7 plus should be a positive point, but it's in the negative space. So this represents negative space, this represents positive, because this is plus 1, this is minus 1. So now we have three errors, right? So this is error 1, error 2, error 3. Okay? Now the question here, should we move the line towards red point or towards the green points?
So is it the absolute error, or I mean just like the numerical value, or is it the absolute one?
So all this, I mean, if you remember, if you go back to the definition of error, so we have absolute value, right? Absolute value.
Okay.
Right? Then should we move this down or should we move up? Yes.
Probably, if there's more, it's like there's more error on the.
Yeah, because we have 2 points, right? So I mean, there are more errors for up above than below, right? So if we move up above, we can reduce more errors. So that's why we can move this above. So what are the good news?
It's like that 2.2 orange red points that will be inside this the margin, right? If we move the region up.
So let me see what will happen if I move this up. Right?
Yeah, that's what I meant. Like, two.
So the good news is this error reduced, right? You follow? But this error increase.
And that two red points that came inside this margin, right? Which shouldn't be the case.
So which means these two also have error,
Yeah.
right? Yeah. I'll adjust this slice. I mean, these two also has error.
Okay.
Yeah. So which means which means if we have multiple misclassified points, then the general idea is we look which side has more misclassified points. So the side with more misclassified points will be the side we move the line towards.
For sure.
Okay? So what's good news?
So, I mean, how far are we gonna move? Like, as we like kind of sort of compromise that 2 points. So what if we compromise more and like move even more towards that?
Yeah. So
center?
how to compromise? This is next component. So the good news is if we do this way, epsilon 8 minus epsilon 5 minus reduce, right? This is epsilon. So this is epsilon 8 minus epsilon 5 minus. They reduce. And unfortunately, the bad news is the error for this point increase. And at the same time, the margin also decreased, right? You see here? The margin was this size, previously it was this size. Okay? So this is the overall idea. So, I mean, if we have a misclassified points, we need to adjust the separating line to reduce the error. But at the same time, we sacrifice the margin size, the margin of our classify. Okay? So which means we need to somehow trade off, right? You follow? So now I'm going to introduce how to trade off the error